What I'm going to talk about is Delta Kernel. And I'm going to talk about, the original title of this was Anatomy of a Delta Connector. What does a Delta Connector built with Delta Kernel look like? But I think a more catchy title is How to Write a Delta Connector in Less than 1,000 lines of code. And that is real, that is not clickbaity, that is real. I'll come to that. Okay, so Delta Connector ecosystem is pretty massive at this point. You can read Delta tables from almost any system you can think of. Now, on one hand, that is absolutely great. Now, on the other hand, there is a huge amount of innovation that continues to happen in Delta. We're working on building new features, crazy new features in the Delta protocol itself to improve and add more functionality that everyone can use. So now, combining this together, we are reaching new frontiers, and new frontiers leads to new kind of challenges. One of the fundamental challenges we are seeing right now is that you have this N connectors that everyone has written for their favorite system, and we are continually making a huge amount of protocol changes in Delta. So that means that it's an N cross M multiplicative complexity for every connector to keep up with the protocol changes if they have to implement those protocol changes from scratch in every connector, like look up the specification, understand it, and implement it and stuff. So this is a problem not many systems around actually have, because either their N is small or their M is small, but we have that. So that's why we have built this new system, new library called Delta Kernel to solve this problem. The goal of Delta Kernel is to be the narrow waist. For those who remember the whole networking stack, TCP/IP, TCP being the narrow waist and stuff, that's the goal, that Delta Kernel provides that narrow interface such that connectors can be isolated from any protocol changes that we're doing below the Delta Kernel. And we've written Delta Kernel is both Java and Rust. That is because Java is for the JVM ecosystem, Spark, Trinos of the world, and Rust is to power the native ecosystem like DuckDBs and the Python libraries, etc. And #GenAI is all about Python. So making it work. So we have written, that's why it's a set of libraries. So it's both available in Java and Rust. Now, you may be sitting here and asking, why should I care? How does it affect me? If you're here, you may be one of three kind of persona here. Either you're a Delta Connector developer that wants to maintain their connector, want to keep up with the latest updates and stuff. So the goal is to make you happy so that you can build your connector. If you're starting a new connector, great, build it using Delta Kernel. You can build it once, and after that, once you build it, you can just keep upgrading the version of the kernel library, and you get the latest and greatest features for practically free. Or if you have a connector already, migrate it into kernel, and then you're good. Or you may be a Delta user, which is more likely the case, that you are a user of Delta tables and you want to access your Delta tables, operate on them from multiple different systems. You will be happy because then all your different systems will stay in sync, that, oh, the latest and greatest features in the protocol are understood by all the systems because all of them are upgraded to the latest version of kernel. So that's great. And then for the small minority of the folks who are Delta protocol developers, who are like, really, I want to build the next generation feature in the Delta protocol, change the protocol in a certain way, do crazy stuff, you will be happy because whatever changes you merge, you will be able to roll out those changes to the end users. Your end users are going to use those changes very, very quickly because you make changes into the specification, you update the kernel, and then we release the kernel and everyone adopts the kernel and new latest features. So this makes, it's a win-win-win. That's the goal. Okay, let's come down to the more basics. This is a library. What is the big deal about this? Why is it so hard to build this? Let's understand the challenges. Why this problem for building a library for Delta tables is particularly unique. There are lots of libraries out there, JSON library, Parquet library. You really don't have to care about what is the exact JSON specification, where should the curly braces be, or you never care about the Parquet library, how it is encoded and stuff. All of that is taken care of by a library. The important distinction is that those are libraries for a file format. CSV, JSON, Parquet, these are file formats. You give it a path to a file or a set of files, you get back the data, that's it. There is nothing more to it. However, things like Delta, Iceberg, Hoodie, these are table formats. There is much more complexity under the hood. For example, for Delta tables, there is a Delta log which keeps track of all the transaction that has happened. You have to read the log, which is the metadata files, and use that information to read the data files. So it's a little bit more complicated than just reading a bunch of data files. Furthermore, if you are reading this library in a single processor, or even a single thread engine, a very simple application and stuff, it is pretty easy actually to build a library like that. You give it a path to the table, the library gives you back, here is the data. That's pretty easy. However, in today's world, you have to deal with distributed engines. And building a library for a distributed engine is much harder. Because in a distributed engine, the same process is not reading the metadata and the data. It's the driver which is reading the metadata to plan out how to split the data reading, etc., into multiple tasks, executors, or multiple threads. Based on the metadata, it will distribute that metadata to the worker nodes, executor nodes, and then the executor nodes will read the data. That is actually definitely much more complicated than a single thread. So to solve these, you have to have the library expose data at the right level of abstraction. For example, just exposing the data is not sufficient. You have to expose the metadata in a certain way. But remember, we want to isolate all connectors from the details of the specification of the Delta protocol. So we don't want to expose the raw metadata that everyone have to really dig deep and understand what the hell is in this metadata. Rather, we want to expose some sort of abstract metadata, which is the connector can consider it as opaque. I don't need to know what's inside that metadata, but I need to be able to split it. For example, to read this particular table, I have to read 100 files. I don't want to know what the content of the file is. Is it Parquet? Is it something else? I don't care. But I need 100 elements that I'm going to send it to 100 different tasks. That is the right level of abstraction here. And so connectors can use these splits and send it to the workers, and so the kernel should be able to also accept a part of the metadata that it provided earlier and read a part of the data, and that's what will happen in the executors. So this is something a lot more interesting than a usual library, which is a challenge. And so the way we've exposed the API is we call this set of APIs table APIs, where you create a table object by providing it a path. I've removed some of the details. I'll fill in a little bit more afterwards. You provide a path that creates a table object. From the table object, you can get a snapshot of your Delta table, either the latest one or time travel, specify a version, specify a timestamp, whatever. And based on that, you can define a scan. If you want to read the table, you can define a scan on that snapshot. And to define the scan, you can specify that I want to query this. I want to query these columns. I want to query based on this filter so that the kernel can figure out, okay, what are the files that you need to read? It can do data skipping, like, okay, these files do not have this data that you're looking for, so I'm not even going to return them at all. So it can do this sort of data skipping, etc., out of the box. So the more information you provide, the more it can help you. And then what it returns is that abstract metadata. Again, I'm not going to go into a lot of details because I'm guessing that, okay, I see laptops open. Somebody might just actually start coding. Sorry about that. I've removed some of the code. So I'll get back to that code once again later. There's a third challenge. No single library is perfect for every possible engine in the world. Because really high performance engines like Spark, Trino, DuckDB, these sort of real engines that really care about the last bit of performance, really like to control tightly their resources, the CPU, the memory, the disk that they use. And so writing a library that works for everything doesn't work best for anything. So what we have to understand is what are the pieces inside the kernel that the kernel has to do that are really resource intensive, like reading Parquet, reading JSON for the metadata files, log files. You have to filter based on the query that, the filter in the query that you have provided in the scan. You have to filter on those statistics of the files, etc. You have to transform the data sometimes, a bunch of things that kernel has to do. So the way to solve this is make kernel actually pluggable. So there's another set of APIs called the engine APIs that the kernel provides, which allows the connector to actually plug in that, okay, I as a connector developer, I want to use the Parquet reader that is already in my engine that already does what is best for the engine. It can read the Parquet file and directly materialize it in memory format that the engine loves, and that is the fastest thing to do. So I can plug in my own Parquet reader. So this engine API actually allows this pluggability into the kernel. What this makes it is that the kernel becomes a very thin layer, and this U-shaped diagram that you see over there, that is the entire connector. The colors are all messed up, so I cannot refer to the colors, but the connector you can see is a U-shape. So the connector controls the top and the bottom of the stack, if it chooses to. And the kernel is just like an orchestrator. It says that, okay, I need to read this file, connector will like, here, I've read it for you, here is the raw data, do whatever you want to do it. Then the kernel will say, oh, I want to modify this file in this way. It'll give it back to the connector, say that, modify it this way and give it back to me. So that gives the connector the entire control of the entire call stack and the entire resource usage of that it can control. So this engine interface has a bunch of pieces inside it. Like there's something called expression handler that allows you to plug in your own expression evaluation engine. That helps for data skipping and stuff like that. JSON handler for reading, writing JSON, file system client for listing the files in the log directory, Parquet handler for reading Parquet. And so going back to the code, remember I created a table object. Now you have to specify an engine to create the table object. This engine, with all these implementations, is what the kernel will use whenever you ask something from kernel. So whenever you want to ask kernel, give me the latest snapshot, it has to use the file system client to list the log directory. It has to use the JSON handler. It has Parquet handler to identify, reconstruct the snapshot. And so that's why every operation to kernel, you provide this engine. And that's how you can plug in your own arbitrary processing logic into the engine itself that the kernel will in turn use. Now, this seems like a pretty complicated interface. Like, do I have to plug in my own Parquet writer, reader every time, JSON reader? This seems pretty complicated. But so the fourth challenge is, how do we keep this thing simple, easy to use for the connected developers? And that's why we are providing our kernel libraries, that's why the set of libraries, bunch of default implementations. You can start with a default engine. Default engine, it works correctly. It will not give you the best performance for your engine, but it will work. That's how you can start off as a connected developer, get all the tests running, everything works correctly, and then you can slowly start taking out pieces and customizing them. For example, oh, I can create a custom engine with only plugs in the custom Parquet handler. Everything else you can keep using the default. Or then I have a better expression evaluator. Let me plug that in. I want to use Arrow for expression evaluation instead of whatever default the Java one provides. And you can plug that in. It can do it completely in incremental manner till the point you get the best performance out of kernel, while ensuring that in future, any kernel upgrades, yes, you're not in the default engine, but if you write your custom engine based on the specifications that you need to satisfy for each of those components, you are still safeguarded, you're future-proof from any protocol changes. At least that's the vision. Okay, I said I walked through different pieces of thing. I talked about different challenges. I want to now talk about how to put these things together. What does it look like? And in the end-to-end, what is the control and data flow here? So let me take the example of a distributed engine. So there's a driver side, which is doing the planning, and then there's the executor side, which is running the tasks and reading the data. There is kernel library to be used on both sides. I guess you can't really see the bottom of the screen, but the left-hand side, the driver side, only is going to read metadata, and the right-hand side is only going to read the data. And since the colors are a bit funky, but I explain things along the way to differentiate. So On the driver side, the first thing that are going to happen is all this file system client, all the engine components are going to be used to read the metadata files and produce in a tabular format the metadata itself, that here are the active set of files in the table that you should read. Then the expression evaluator comes in, that is used to apply the query filter that you provided us to do additional data skipping, to eliminate files that doesn't have your data. So that ultimately produces the metadata that the connector needs to use. And so this metadata itself is in a tabular format. It's in the form of columnar batches or whatever format in memory representation that your custom Parquet handler or custom engine implementation that the connector understands, that is the in-memory representation. And now the connector can either take this table of metadata, split it by the rows, and send it to all the executors. So it's the connector's responsibility to take this abstract metadata. It doesn't need to understand what is inside it. It can just need to split it and serialize it and send it to the executor. The executor plugs that part of the metadata it received back into the kernel. And then again, the Parquet handler comes into the picture. It reads up the raw data from the Parquet, gives it to the kernel. The kernel again uses expression evaluator to do things like filtering by DVs, or there are concepts like generated columns, where at the read time you automatically generate a column based on an equation, and then finally produce the final table data for the connector to use. I see you're taking photos, but the reality of this thing is that you don't need to really understand this. Because all you need to understand is, here I'm getting back a bunch of metadata, I need to split it, send it, serialize it, send it over, and feed it back. That's all you need to understand. That's the best part about this. So that won't come to the test. Okay, all this is great. The question is this real? Who is using kernel right now? We released this idea of this new project initiative last year. How far have we progressed in this last year? The first release came in October. The kernel Java in Delta 3.0 was the first release in October, so it's been 8 months. There's been a lot of progress. Oh, wow, the colors are fantastic. Okay, so on the Java side, there has been a lot of progress. A lot of logos here, continues to grow. Some of them have already released their connector based on kernel. Some of them are in progress. We are closely partnering with them. But let me walk through some of the case studies. Druid was absolutely the first one to use kernel in Delta 3.0 to add their first Delta support, their new Delta connector. And you can look at their PR, which added the Delta connector. It is less than 1,000 lines of production code. Testing is probably 500, 600 more lines. And then the total PR is around 200, 2,300, which includes POM, XML, and other crap. So production line of code is less than 1,000 lines of code. This is the power of kernel, that it abstracts out everything using these relatively narrow, not the most narrow, because you still have to deal with metadata and stuff, but still it's not a lot of code that you can, and you get your brand new Delta connector. And they have been based, and what we had promised is that you should be able to upgrade to the latest kernel version every time we make a release and get support for it. They have been doing exactly that. They have already, Delta 3.2 came out last month. Yeah, early May, and they've already upgraded to 3.2. So that's great. And so 3.2 came out with the latest protocol, Checkpoint V2 supports. I guess they already support reading liquid tables. You have heard all of these names, liquid tables. They already support reading these liquid tables and stuff. The other one, we're very excited about this because this came out a couple of weeks back, is DuckDB. We worked with the DuckDB folks. We co-developed the Delta kernel in Rust in such a way such that it can be used, even though kernel is in Rust, there is a CFFI layer such that it can be used from DuckDB, and DuckDB can call into kernel Rust from their C++ code. So it was really a massive joint effort, and it worked out because DuckDB, you can download DuckDB Delta connector right now. Actually, you don't even need to download. If you just take brew install DuckDB, just install DuckDB and just say select star from, wow, it's covered. The select star from Delta scan table path, it will just work. It will automatically download the Delta connector and it will just work. This is exciting. And then there is existing connectors being continuously improved by moving over to kernel. Apache Flink, we suppose writing to Delta, reading from Delta, streaming fashion, batch fashion. We understand it takes quite a bit of effort to migrate something that is existing to something completely new with a slightly different architecture, different model of how to do things and stuff. So it's a process. And we've started that process. We have taken already pieces of the Delta Flink connector and replacing it with kernel. And we're already seeing massive benefits. So while the full, like migrating the entire Delta Flink sync to purely use kernel is in progress, the piece that we already did is initializing the Flink sync to quickly understand this is the schema of the Delta table that itself, that was taking a huge amount of time when the table was very, very large. We were trying this on a 11 petabyte table with 7 million files. Not a joke. So there, just replacing the earlier Delta standalone, if some of you might be familiar with Delta standalone is the Java library that existed before Delta kernel. That is like a philosophical precursor to Delta kernel. Delta standalone, we didn't quite get things right. Delta kernel is the way we are getting things right in abstracting out everything to isolate the connectors from protocol changes. So we are migrating from standalone to kernel, and it gave a 45x improvement because kernel allowed reading the basic metadata of the table from the log files, like the schema of the table and stuff like that, much, much, much faster, 45x faster. Another one, it's a partnership going on right now between Startree and Pinot. Startree folks, and they migrated their connector again from standalone to kernel. And what the benefit they got is that earlier, since they were using standalone, they had to disable deletion vectors. Standalone doesn't support deletion vectors. They had to disable deletion vectors for their customers, but with kernel, they won't have to do that anymore. So benefit all over the place. And kernel also is enabling a fundamental new architectures. Because, for example, how many people here know about Delta sharing? Okay, some don't. Okay, so here's a 30-second overview. Delta sharing is a protocol by which a Delta sharing server can share the information of a Delta table to a client. So what the server does, it reads the Delta table's metadata and sends that metadata over to the Delta sharing client in the form of pre-signed URLs. But basically, here are the bunch of Parquet files you need to read this Delta table. So it sends a pre-signed URLs of those Parquet files to the client. So the client doesn't need to understand the Delta table. It can just read the pre-signed URLs data, and it just gets the table, gets the table data. Pretty popular system for sharing clients, very successful. But it was suffering through the same challenges of keeping up with the Delta protocol. Like earlier, before deletion vectors, Delta was just a bunch of Parquet files. This thing perfectly worked. But with deletion vectors, you're saying, here is a Parquet file, here is a bitmap deletion vector, which identifies which rows have been logically deleted. So it's not a list of Parquet files anymore. You need to do a lot more to understand DVs and if you ignore the DVs, you're reading wrong data on the client side, because data rows that have been deleted logically will be read. You don't want that. So that was one challenge. And two is the general challenge of keeping up with the next. The deletion vector was just one of them. Like how do you keep up with all the protocol changes and stuff, liquid tables, etc. So we sat down, we went back to the drawing board and came up with a completely new architecture where instead of sharing the table as a list of Parquet files, we share it as the Delta log itself. The server reads the log and just shares the log in plain text. Like, here is the full log details. Client, you figure out how to read this Delta table. So well, it's not unmodified. So the log has all the file names are replaced by pre-signed URLs, but rest of the metadata of here is a deletion vector, here is a Parquet file are all sent over. It's the client's responsibility to read it as a Delta table. And so on both sides, the server side, Delta sharing server is going to use the kernel to read the Delta table. And on the client side, they are also going to use the kernel to read the Delta table. One of the first set of things that are going to come out is Delta sharing server is going to migrate to the kernel Java, and Delta sharing Pandas client is going to migrate to the Delta kernel Rust. Over the next couple of months, both of them are going to come out. But with this new architecture, Delta sharing as a protocol built on top of Delta tables is fully future-proof, because whatever protocol changes that goes in Delta, sharing server doesn't need to be updated. It just needs to upgrade the kernel. Kernel will expose the metadata. It just needs to identify which are file names, Parquet file names or deletion vector file names, just re-encode them into pre-signed URLs and then send it over. Everything else, Delta sharing is completely agnostic to. Okay, this is a very important call to action. If anybody here or whoever is viewing over YouTube or whatever, if you're using Delta standalone is going to get deprecated. So you should start migrating to Delta kernel. Pretty much 99% of all functionality right now available in Delta standalone, what you could have done, can be done in Delta kernel right now. We are there. So we are very close to deprecating of Delta standalone. So what does the future look like? That was a glimpse into the future, that standalone is going away, kernel, but let's talk a little bit more. So yes, we have a pretty long roadmap, because what we started this project is like a re-implementation of the Delta protocol from scratch. And there is like 5-6 years worth of Delta protocol changes that we are catching up with. And so it's both we are catching up to what is our backlog, as well as new protocols are being built right now. There are 7 protocol RFCs in flight right now. We're also working with the developers to build functionality directly into kernel as well. So the Java is a little bit ahead, Rust is following pretty closely, but we'll keep working through this, and at some point we will reach parity, that all the previous protocols are supported in kernel, both Java and Rust, and new protocols are going to get added. And that is a fundamental paradigm shift in the protocol design itself, because now there is a symbiotic relationship between the protocol and kernel. As we design, anyone who is designing a new protocol has the responsibility of implementing in kernel if they want their protocol to be actually used by users. So new protocols will be implemented in kernel, but in the design process itself, if your protocol design if your proposal is not such that it can be implemented in the kernel architecture, that means that your protocol design is not good. So the kernel architecture itself feeds back into the protocol design process, and how do you design a protocol that can be implemented in the kernel architecture such that connectors don't need to change. It can be shielded by kernel. So this is a new paradigm shift for the future of Delta project fundamentally, that kernel is the underpinning of that. And you can contribute. There's more than 15 plus developers have contributed across Java and Rust, and a lot of them are actually outside Databricks. So it's great because it's a completely clean slate implementation. You don't need to have knowledge of like 20,000, 50,000 lines of code base to really make any changes. You can just, here's like few thousand lines of code. Let's just understand that and start implementing. What we do is we create good first issues for both on the Java side and the Rust side, so you can just pick up and start implementing small pieces here and there. The future, what we hope to achieve, is that kernel is the center and everybody can interoperate with, give everybody else with Delta kernel. That's it.